1920, Chicago rail yard. Two excavating machines dig side by side in the morning frost. The 70-ton Marion steam shovel hisses and clanks, burning 4,000 pounds of coal and 800 gallons of water every 10 hours. 12 men sweat to keep it running, firemen stoking coal, engineers monitoring pressure gauges, track crews laying steel rails wherever it needs to move. 50 feet away, a compact Orton gasoline shovel purrs quietly on its tracks. Two operators, 5 gallons of fuel per shift, moving nearly the same amount of earth at 1/10 the cost. European engineering experts had spent 80 years perfecting steam excavation technology. Bigger boilers, more pressure, heavier machines. They insisted that serious digging required massive steam power, 180 pounds per square inch, to generate the 200 horsepower needed for industrial excavation. American contractors were about to prove them completely wrong, not with more power, not with bigger machines, but with mechanical intelligence that would make the most advanced European steam technology look like expensive, complicated relics from a dying era. The breakthrough began not in a corporate boardroom or university laboratory, but in the practical mind of Oliver Steinbrenner as he watched steam shovels struggle through another Chicago winter morning in 1918. While his competitors at Marion and Bucyrus focused on building ever larger steam monsters, Steinbrenner approached excavation from the opposite direction. What if the problem wasn't insufficient power, but wasted power? Steam shovels operated on a fundamentally inefficient principle that had remained unchanged since William Otis's 1839 patent. Coal burned in fireboxes heated water in massive boilers, creating steam at 180 pounds per square inch. This steam then traveled through pipes to drive pistons that operated cable drums through complex mechanical linkages. At each stage, combustion, steam generation, transmission, and mechanical conversion, energy hemorrhaged away as waste heat. A typical Marion steam shovel consumed 4,000 pounds of coal per shift, but delivered perhaps 40% of that energy to actual digging. Steinbrenner's insight was deceptively simple: eliminate the middleman. Instead of burning coal to make steam to drive cables, why not use a gasoline engine to directly power mechanical winches through precision gear reduction? The mathematics were compelling. A 40 horsepower automobile engine could deliver 30 horsepower directly to the digging mechanism, while a steam shovel's theoretical 200 horsepower dwindled to perhaps 80 usable horsepower after transmission losses. The engineering challenge lay in mechanical precision rather than brute force. Steam systems relied on massive weight and momentum to power through resistance. When a steam shovel's bucket hit hard-pan clay, operators simply increase boiler pressure and let physics do the work. Steinbrenner's gasoline-powered machine weighed 15 tons versus steam shovels' 70 tons, requiring entirely different mechanical solutions. His breakthrough came through what he called intelligent gearing. Instead of fixed-ratio cable drums, Steinbrenner designed a system of variable mechanical advantage that automatically adjusted to digging conditions. In soft soil, high-speed gearing allowed rapid bucket movement with minimal fuel consumption. When resistance increased, the operator could shift to low-speed, high-torque gearing that concentrated the engine's full power into precise digging force. The first Orton Model T crawler crane emerged from the company's Chicago workshop in spring 1919, looking nothing like established excavation equipment. Its riveted steel construction housed exposed dual drums positioned outside a compact operator cab, eliminating the massive boiler house that dominated steam shovel design. The live roller circle bearing allowed smooth rotation without the complex cable and pulley systems that frequently jammed on steam machines. Most revolutionary was its operational simplicity. Steam shovels required 2 hours of careful firing to build working pressure, during which firemen monitored coal quality, water levels, and steam temperature with constant vigilance. A single operator error could cause explosive boiler failure or costly pressure loss that halted work for hours. Steinbrenner's gasoline machine started with the turn of a key and reached full operating power within minutes. The prototype's first commercial test came that spring on a modest Chicago basement excavation project. The job called for moving 150 cubic yards of mixed soil and clay, exactly the type of small-scale work that made steam shovels economically impractical. A 70-ton Marion would require railroad tracks laid to the site, a 12-man crew, coal delivery, and water supply for what amounted to 2 days of actual digging. The Orton crawler simply drove to the job site under its own power. 2 operators, an engineer, and an oiler began digging immediately. Working steadily through an 8-hour shift, they moved 150 cubic yards of material while consuming exactly 4 gallons of gasoline. The same job would have required a steam shovel to burn nearly 2 tons of coal plus 800 gallons of water. Word spread quickly through Chicago's construction community. Contractors who had dismissed gasoline excavation as underpowered began requesting demonstrations. The numbers were undeniable: 3-to-1 fuel efficiency, 10-to-1 crew size reduction, and immediate operational readiness without steam uptime or infrastructure requirements. Henry Barnhart, the respected steam shovel designer who had partnered with Edward Huber to improve bucket support systems, visited Steinbrenner's workshop that summer. What he found challenged everything he understood about excavation engineering. "This machine accomplishes more actual digging per dollar spent than anything I've operated in 30 years, he admitted to colleagues. "It's not about horsepower, it's about applying that power intelligently." By autumn 1919, Orton and Steinbrenner had received inquiries from contractors across the Midwest. Small builders who couldn't justify $15,000 steam shovels for residential foundations suddenly had access to efficient excavation at 1/10 the operating cost. The gasoline advantage extended beyond fuel efficiency to operational flexibility. These machines could work anywhere, wheeled vehicles could travel, unconstrained by railroad infrastructure or water supplies. The engineering revolution was mechanical rather than metallurgical. While European manufacturers continued pursuing higher steam pressures and larger boiler capacities, American ingenuity had discovered that excavation efficiency came through precision rather than power. Steinbrenner's compact machine concentrated its energy more effectively than machines 5 times its weight, proving that American practical engineering could outperform European theoretical approaches through intelligent design rather than overwhelming force. The stage was set for gasoline excavation to transform American construction, though neither Steinbrenner nor his competitors yet understood how dramatically this mechanical intelligence would reshape the entire industry. The first major validation of Steinbrenner's gasoline technology came through an unlikely source: Thomas "Steam Tom" McKenna, a veteran engineer whose reputation had been built on 15 years of operating the most complex steam shovels from the Pennsylvania coal fields to the Panama Canal. McKenna arrived at the Chicago rail yard that spring morning in 1919, expecting to witness another failed American attempt to challenge proven European steam engineering. What he found instead forced him to question everything he had learned about excavation power. The Orton Model T sat quietly beside his familiar Marion steam shovel, its compact frame dwarfed by the massive boiler house and smokestack that had defined serious digging equipment for 8 decades. While McKenna's crew spent 2 hours building steam pressure, checking water levels, and stoking coal to operational temperature, the gasoline machine's operator simply turned a key, adjusted the throttle, and began digging. McKenna watched with grudging fascination as the lightweight machine's bucket bit into hard-packed clay with precision that his steam-powered cables couldn't match. The gasoline engine's constant torque eliminated the surging, jerky motion that characterized steam operation, allowing smooth bucket control even in difficult material. "That machine moves like it's thinking about the dirt," McKenna admitted to his firemen. "Steam power fights the ground. This thing seems to work with it." The performance comparison became stark as the morning progressed. McKenna's steam shovel moved 200 cubic yards while consuming nearly half a ton of coal and 400 gallons of water. The Orton machine excavated 180 cubic yards on exactly 4 gallons of gasoline, operated by a single engineer who never left his seat to adjust fuel, monitor pressure, or coordinate with ground crews. Big Jim O'Malley, the construction foreman supervising the rail yard expansion, had spent his career calculating costs in cubic yards per dollar rather than theoretical horsepower ratings. His weathered notebook contained 15 years of excavation data from dozens of job sites, and the numbers emerging from this comparison defied everything he understood about equipment economics. Steam shovels cost me $12 per hour to operate, counting coal, water, and crew wages, he explained to visiting contractors. That gasoline machine is running at $2 per hour and digging almost as much dirt. The breakthrough extended beyond simple fuel efficiency to operational reliability that steam technology couldn't match. Steam shovels suffered constant mechanical failures as extreme pressure stressed boiler tubes, valve seats, and cable systems. A typical Marion required 2 hours of daily maintenance for every 8 hours of operation, with major overhauls every 6 months as salt deposits and thermal cycling degraded critical components. Steinbrenner's gasoline machine operated for weeks with basic lubrication and fuel. Its mechanical simplicity eliminated hundreds of failure points that plagued steam systems. No boiler tubes to leak, no steam valves to jam, no complex cable arrangements to stretch and break under load. The machine's reliability allowed contractors to schedule excavation work with confidence instead of building buffer time for inevitable steam shovel breakdowns. Edward Huber, who had co-founded Marion Steam Shovel Company and understood excavation economics better than any manufacturer in America, visited Chicago that summer to evaluate the gasoline threat to his established business. What concerned him wasn't the Orton machine's immediate performance, but its economic implications for the entire industry. This technology changes the fundamental mathematics of excavation, Huber confided to his chief engineer after 3 days of field observation. We've built our business selling $15,000 machines to large contractors who can afford the infrastructure and crew costs. Gasoline shovels will cost $3,000 and allow small builders to compete for jobs that require excavation. We're not just facing a superior product, we're facing a completely different market structure. The gasoline advantage became most apparent on smaller projects where steam shovels proved economically impractical. A typical residential foundation requiring 50 cubic yards of excavation couldn't justify the expense of railroad track installation, coal delivery, and 12-man crews that steam operation demanded. Contractors either excavated by hand with immigrant labor gangs or avoided projects requiring significant earth moving. Gasoline excavation opened entirely new market segments to mechanical digging. The Orton machine could drive directly to residential job sites, begin working immediately, and complete foundation excavation in hours rather than days. Small contractors who had never owned mechanical equipment suddenly could afford efficient excavation, fundamentally altering the competitive landscape of American construction. Daniel P. Eales, whose Bucyrus company had dominated heavy excavation since 1880, initially dismissed gasoline technology as suitable only for light residential work. His company's massive steam shovels moved mountains in mining operations and cleared railroad rights-of-way across continental distances. Surely serious industrial excavation would always require the raw power that only steam pressure could provide. Yet even Eales couldn't ignore the operational data emerging from Chicago. Gasoline machines worked in conditions that defeated steam shovels, remote locations without water supplies, urban sites where coal smoke violated city ordinances, and projects where rapid setup and breakdown eliminated weeks of preparation time. The technology's flexibility was revealing limitations in steam operation that had been accepted as inevitable constraints of mechanical excavation. By autumn 1919, Orton and Steinbrenner had received orders for 12 machines from contractors across Illinois, Indiana, and Ohio. Each successful installation generated additional interest as builders discovered that gasoline excavation eliminated not just fuel costs, but the entire infrastructure burden that made steam shovels practical only for large-scale projects. The revolution was gathering momentum through economic logic rather than engineering superiority. American practical innovation had found a way to make mechanical excavation accessible, affordable, and reliable for the vast majority of construction projects that steam technology had priced out of the market. The disaster that nearly destroyed gasoline excavation began with overconfidence born from 6 months of flawless performance. When Chicago's Union Station announced its massive foundation excavation project in October 1919, Orton and Steinbrenner saw an opportunity to prove their technology could handle the heaviest industrial work. The contract called for moving 12,000 cubic yards of mixed soil and clay hardpan in 60 days, exactly the type of large-scale project that had been steam shovel territory since the 1840s. Three established steam shovel contractors submitted bids using proven Marion and Bucyrus machines. Their proposals detailed familiar logistics, railroad spur construction, coal, supply arrangements, waterline installation, and 12-man crews working 10-hour shifts. Total excavation cost: $48,000 including equipment, fuel, and labor. Steinbrenner's bid shocked the construction industry. $18,000 using two gasoline-powered Orton machines with 4-man crews. The savings came entirely from operational efficiency, no infrastructure preparation, minimal fuel consumption, and crews one-third the size of steam operations. If successful, the project would establish gasoline excavation as viable for the largest American construction projects. Daniel P. Eales viewed the Union Station competition as an opportunity to crush gasoline technology before it threatened Bucyrus's dominance in heavy excavation. His company deployed their most powerful steam shovel, a 75-ton monster capable of moving 300 cubic yards per 10-hour shift when operating at full capacity. "Let's see how those toy machines perform against real excavation equipment," Eales told his foreman as the massive Bucyrus rumbled into position beside the much smaller gasoline shovels. The first week vindicated gasoline efficiency. Working in relatively soft topsoil, both Orton machines maintained steady production while consuming 5 gallons of fuel per shift. The steam shovels required constant attention from firemen monitoring boiler pressure and coal quality, with frequent stops to adjust cable tension and clear debris from complex mechanical linkages. By Friday, the gasoline machines had excavated slightly more material at half the fuel cost. Steam. Tom McKenna, operating the lead Bucyrus machine, grudgingly respected the gasoline shovel's consistent performance, but remained confident that serious digging would expose their limitations. "Wait until we hit hardpan," he told his crew. "Steam pressure and machine weight are what move tough material. Those lightweight machines will bog down when the real work starts." The hardpan layer began 18 feet below grade, dense clay compressed by geological pressure into material nearly as hard as soft rock. Steam shovels attacked such conditions with brute force, using massive weight and 200 horsepower steam pressure to fracture resistant material through repeated impact. Experienced operators like McKenna knew how to coordinate boiler pressure, cable tension, and bucket angle to break through the toughest excavation challenges. Steinbrenner's gasoline machines met the hardpan on Monday morning of the second week. Their lightweight construction and 40 horsepower engines seemed laughably inadequate against material that regularly broke steam shovel cables and bent reinforced steel buckets. Yet for the first 4 hours, intelligent gearing and precise mechanical control allowed steady progress through conditions that would challenge much larger machines. The catastrophic failure began gradually, almost imperceptibly. Working in clay that required maximum engine output for every bucket load, both gasoline machines began running hotter than normal operating temperatures. The air-cooled engines, designed for intermittent high-power work typical of road construction, couldn't dissipate heat generated by constant full-throttle operation in resistant material. By noon, white smoke began rising from the lead machine's engine compartment. The operator, pushing to maintain production schedules, continued digging as cylinder temperatures climbed beyond safe limits. Steam shovels could work indefinitely at maximum power because their boiler systems were designed for sustained high-temperature operation. Gasoline engines had no such thermal reserves. At 2:15 in the afternoon, the lead Orton machine's engine seized completely. Pistons locked in overheated cylinders as metal expanded beyond design tolerances. The machine sat motionless in 18 feet of excavation, its compact frame dwarfed by the massive hole it had helped create but could no longer escape. The second gasoline shovel suffered identical failure within an hour. Both machines became expensive monuments to the limitations of lightweight excavation equipment in industrial conditions. Steam shovels continued working steadily, their massive boilers and heavy construction proving superior to gasoline efficiency, when sustained power became more important than fuel economy. Big Jim O'Malley watched the recovery operation with grim satisfaction. Steam-powered cranes hauled the disabled gasoline machines from the excavation while McKenna's Bucyrus resumed steady production in the hardpan. "I wanted those gasoline shovels to work," O'Malley admitted to reporters. "But you can't fool physics. Heavy digging requires heavy equipment, and there's no substitute for proven steam power when conditions get tough." The Union Station disaster validated every criticism that established manufacturers had leveled against gasoline excavation. Orders for Orton machines evaporated overnight as contractors concluded that gasoline technology might work for light residential projects, but lacked the power reserves necessary for serious industrial excavation. Steinbrenner's company faced bankruptcy as word spread through the construction industry that gasoline shovels couldn't handle real digging conditions. Daniel P. Eels seized the moment to reassert steam supremacy. "This unfortunate incident proves what Bucyrus has maintained from the beginning," he announced in Engineering News Record. "Excavation is heavy work requiring heavy machinery. Gasoline engines may power automobiles adequately, but they cannot replace steam power for industrial applications." The failure seemed to confirm European engineering wisdom that had dominated excavation technology for 8 decades. Serious digging required massive boiler pressure, heavy machine construction, and the thermal capacity that only steam systems could provide. American ingenuity had challenged established principles and been found wanting when subjected to real-world industrial conditions. Yet in his Chicago workshop, Oliver Steinbrenner was already analyzing the failure and designing solutions that would transform the disaster into the foundation for gasoline excavation's ultimate triumph over steam technology. The solution that would revolutionize American excavation emerged not from Steinbrenner's engineering calculations, but from a casual observation made by his shop foreman while examining the seized engines from Union Station. "These cylinders locked up because they were working too hard for too long," the foreman noted, running his fingers along the warped metal. "Steam shovels don't have this problem because they automatically work easier when they hit resistance. The steam just bleeds off pressure. Maybe we need to make gasoline engines work smarter, not harder." This insight sparked Steinbrenner's breakthrough. What if gasoline excavation could automatically adapt to digging conditions instead of fighting them with constant maximum power? Steam shovels achieved this adaptation through pressure relief valves that reduced power when resistance increased, protecting the system from overload. Gasoline engines needed a mechanical equivalent, a way to sense load conditions and adjust power delivery accordingly. Working through the winter of 1919 and 20, Steinbrenner developed what he called his load-sensing mechanical system. The innovation centered on a governor mechanism that monitored engine RPM under load. When the bucket encountered easy digging conditions, the system maintained high engine speed and rapid hydraulic flow for maximum productivity. But when resistance increased, indicating hard material or overload conditions, the governor automatically reduced engine RPM while shifting transmission gearing to multiply torque output. The mechanical genius lay in making this adaptation seamless and automatic. Unlike steam shovels, where operators constantly adjusted throttles and pressure settings based on experience and intuition, Steinbrenner's system responded instantly to changing conditions without human intervention. The engine essentially learned to work efficiently across the full spectrum of excavation challenges. The thermal management solution proved equally innovative. Instead of trying to build more cooling capacity into compact engines, Steinbrenner redesigned the entire power delivery system to eliminate sustained high RPM operation. His load-sensing governor ensured that engines never worked at maximum output for extended periods, automatically reducing power demands before dangerous temperatures could develop. Henry Barnhart, whose reputation for practical engineering solutions had made him a respected voice in excavation technology, visited Steinbrenner's workshop in March 1920 to evaluate the improved design. What he found challenged fundamental assumptions about excavation power. "This machine doesn't just dig," Barnhart observed after watching the prototype operate. "It thinks about digging. It adjusts its own power to match conditions I've never seen any excavation equipment handle automatically. The key breakthrough was philosophical rather than mechanical. While steam shovels relied on overwhelming force to power through resistance, Steinbrenner's improved system used mechanical intelligence to work efficiently within material limitations. Instead of fighting hardpan clay with brute force, the load sensing system automatically downshifted to high torque, low speed operation that concentrated available power precisely where needed. Field testing began in April 1920 on a suburban Chicago drainage project that presented exactly the mixed conditions that had destroyed the original Union Station machines. The job site contained layers of soft topsoil, packed clay, and occasional hardpan sections, a perfect proving ground for the adaptive technology. The results astonished even Steinbrenner. Working in soft soil, the machine automatically maintained high productivity with minimal fuel consumption, completing easy excavation at rates that matched the original prototypes. But when the bucket encountered hardpan, instead of bogging down or overheating, the load sensing system instantly shifted to maximum torque output while reducing engine stress. Most remarkably, fuel consumption remained almost constant regardless of material difficulty. The automatic power management meant the engine worked efficiently across all conditions rather than alternating between idle and maximum output like traditional excavation equipment. A full day of mixed excavation, including 4 hours in difficult hardpan, consumed exactly 5 3/4 gallons of gasoline. Thomas McKenna, whose steam shovel expertise had made him skeptical of gasoline technology, witnessed one of the first demonstrations with grudging professional interest. The mechanical sophistication impressed him more than raw power specifications. This machine operates like a skilled steam engineer is constantly adjusting its performance, McKenna admitted. But it's doing automatically what takes me 15 years of experience to do manually. The breakthrough extended beyond individual machine performance to operational philosophy that would reshape American construction. Steam excavation required skilled operators who understood complex mechanical systems and could coordinate multiple variables: boiler pressure, steam flow, cable tension, and bucket control. Steinbrenner's load-sensing technology made efficient excavation accessible to operators with basic mechanical skills. Edward Huber recognized immediately that this development threatened not just steam technology, but the entire skilled labor structure that supported heavy excavation. If any competent equipment operator can run these machines efficiently, we're facing more than technological competition, he warned fellow steam shovel manufacturers. We're facing democratization of excavation capability. Word of the improved technology spread quickly through construction networks as contractors who had witnessed the Union Station failure began requesting new demonstrations. The load sensing system addressed every criticism that had been leveled against gasoline excavation: insufficient power in difficult conditions, operator skill requirements, and reliability under sustained industrial use. By summer 1920, orders for the improved Orton machines began arriving from contractors who had previously dismissed gasoline technology. The automatic adaptation meant these machines could handle any excavation project that didn't specifically require the massive scale of railroad-mounted steam shovels while maintaining the fuel efficiency and operational simplicity that made gasoline attractive for smaller projects. Daniel P. Eels, whose Bucyrus company had celebrated gasoline excavation's apparent defeat at Union Station, began receiving disturbing reports from field representatives. Contractors were choosing gasoline machines for projects that traditionally used steam equipment, not because of lower initial cost, but because of superior operational efficiency under real working conditions. The stage was set for a fundamental shift in American excavation technology, driven not by more powerful equipment, but by mechanical intelligence that made efficient digging accessible to the entire construction industry. The vindication Oliver Steinbrenner had worked 18 months to achieve came in September 1920, when Chicago's Union Station project managers announced a rematch competition. The same hardpan excavation that had destroyed his original machines now offered an opportunity to prove that mechanical intelligence could triumph where brute force had failed. This time, however, the stakes extended far beyond a single construction contract. The entire future of American excavation technology would be determined by performance in the clay that had humbled gasoline power 1 year earlier. Daniel P. Eels approached the rematch with supreme confidence. His Bucyrus steam shovels had completed the original Union Station excavation flawlessly after the gasoline machines failed, establishing steam power's superiority in industrial conditions. "We're facing the same physics that defeated these machines before," Eels told his chief engineer. "Clay hardpan requires sustained high power output, and there's no substitute for steam pressure when conditions demand maximum performance." The competition parameters seemed designed to favor steam technology. 12,000 cubic yards of mixed excavation, including the notorious hardpan layer that began 18 feet below grade. 60-day completion deadline. No allowances for equipment failure or weather delays. Steam shovels entered the contest with proven track, records, experienced crews, and the mechanical reserves necessary for sustained heavy-duty operation. Steinbrenner's improved Orton machines arrived at the job site, looking deceptively similar to the failed prototypes. The critical differences were invisible: internal governor mechanisms, load-sensing transmission systems, and thermal management protocols that would automatically prevent the overheating that had doomed the original attempt. Only field testing would reveal whether mechanical intelligence could overcome the fundamental power limitations of lightweight gasoline equipment. Big Jim O'Malley, whose 15 years of construction experience had taught him to trust proven technology over promising innovations, supervised the rematch with skeptical attention to detail. His weathered notebook contained performance data from dozens of excavation projects, and the numbers consistently favored steam power for sustained industrial work. "I want these gasoline machines to succeed," he confided to visiting contractors. "But physics doesn't care about fuel costs when you need to move dirt efficiently." The competition began in familiar topsoil conditions where gasoline efficiency had always excelled. Both Orton machines maintained steady production while consuming 5 gallons of fuel per 10-hour shift, operated by 2-man crews who never left their seats to adjust mechanical settings or coordinate with support personnel. The steam shovels required their traditional 12-man crews, including firemen, engineers, and maintenance specialists, burning nearly 2 tons of coal daily while achieving comparable excavation rates. Thomas McKenna, operating the same Bucyrus machine that had outlasted the original gasoline shovels, watched the improved Orton equipment with professional curiosity rather than concern. "They're digging well in easy conditions," he acknowledged to his firemen, "but we'll see what happens when they hit real resistance. Steam power doesn't depend on fancy mechanical systems. It just keeps working when conditions get tough." The critical test arrived on Monday morning of the second week, when both excavation teams reached the hardpan layer. This was the material that had seized gasoline engines through sustained maximum power operation, validating steam technology's thermal superiority. McKenna's steam shovel attacked the resistant clay with familiar brute force techniques, using 200 horsepower steam pressure and 75-ton machine weight to fracture hardpan through repeated high-impact bucket loads. Steinbrenner's load-sensing machines responded differently. Instead of fighting the hardpan with constant maximum power, the governor systems automatically adjusted engine RPM and transmission gearing to optimize torque delivery for resistant conditions. The engines worked steadily, but never at the sustained high output that had caused catastrophic overheating during the original competition. The results became apparent within hours. While steam shovels maintained their traditional excavation rates in hardpan through sheer mechanical force, the gasoline machines achieved nearly identical productivity through intelligent power management. More significantly, engine temperatures remained within safe operating ranges throughout 10-hour shifts in the most demanding material conditions. Henry Barnhart, whose practical engineering experience made him a respected evaluator of excavation equipment, documented the performance comparison with meticulous precision. "The gasoline machines are excavating 200 cubic yards per day in hardpan conditions while consuming 5.5 gallons of fuel," he reported to industry publications. "Steam shovels are achieving 210 cubic yards daily while burning 4,000 pounds of coal. The efficiency difference has become overwhelming." The breakthrough extended beyond individual machine performance to crew productivity and operational reliability. Steam shovels required constant attention from skilled specialists who understood complex boiler systems, steam flow dynamics, and cable tension management. Equipment failures occurred regularly as extreme pressures stressed mechanical components, requiring immediate repairs to maintain production schedules. Steinbrenner's load-sensing machines operated with unprecedented reliability. The automatic power management eliminated operator errors that typically caused equipment overload, while mechanical simplicity reduced failure points by eliminating hundreds of components required for steam generation and pressure control. Excavation continued steadily, with minimal maintenance beyond daily lubrication and fuel replenishment. Edward Huber visited the job site during the third week of competition with growing concern about implications for his Marion Steam Shovel Company. What he observed challenged fundamental business assumptions that had supported steam excavation for 8 decades. These gasoline machines are proving that mechanical intelligence can replace raw power in industrial applications, he confided to his chief engineer. If this technology spreads, we're facing obsolescence of our entire product line. By the competition's conclusion, the performance data demonstrated gasoline excavation's complete transformation from novelty to industrial necessity. The improved Orton machines had moved 12,000 cubic yards of mixed material while consuming 330 gallons of gasoline total, equivalent to less than 1 day's coal consumption for comparable steam equipment. The vindication was absolute. Mechanical intelligence had overcome every limitation that critics had identified with gasoline excavation, proving that American practical innovation could solve complex engineering challenges through design sophistication rather than overwhelming force. The future of excavation technology would be determined not by the largest machines, but by the smartest ones.